Good, let's begin. Hi everyone. So today's talk is going to be about 3D graphics using a library called Threejs. So what is Threejs? Well, Threejs is a JavaScript library. It's MIT licensed, so you can use it as you like. And it basically creates a nice layer of abstraction over something that is actually quite complicated. For those of you who have done graphics with, say, with WebGL, for example, you will know that it takes a lot of code and mathematics to do even the most basic things. The power of Threejs, and what I really enjoy about it and using it, is that it makes doing things that are really complicated really simple. And that's a great thing, right? So let's see what I'm talking about. So it all begins with this, a tree. You can almost think of this like the DOM. It's the DOM of Threejs. This is where you put all the information that you're ever going to have about your environment, your 3D environment. Every object that's going to be in there, every person, every car, every gun, every plane, every tree, everything you're going to have in your three-dimensional environment, you're going to add as objects in this tree, okay? Now, what's interesting about this tree is, of course, it's a hierarchical tree, which means an object can have children. Why is this important? Composition. If you think about it, for example, let's say you want to represent a car, right? So you might have an object abstractly representing a car, but a car is not one thing. A car has wheels, right? A car has the front, it's got the lights, it's got all these different parts. So you could theoretically imagine all of these things as being objects, which can be added together in this hierarchy to form a car. Cool? Now, at the top of the hierarchy is an object called scene. Now here's the thing. You see object 3D? Object 3D is like an abstract class. I know we don't have like abstract classes or whatever in JavaScript, but you guys all know what I'm talking about. You can think of it like an abstract class. It's not meant to be used directly. You can use subclasses. Scene is a subclass of object 3D. Okay, so scene is itself an object 3D. And an object 3D, like I said, is just a member of a hierarchy, which means it can have children and potentially one parent. Cool? All right. Now, a little bit of code, all right? So what you can do with these objects is you can move them in your scene. You can position them. You can say where you want them to be in your three-dimensional world. And because we're living in a three-dimensional world, you have to specify X, Y, and Z. Fine. You can also specify the rotation, how you want the object to rotate, where you want it to face in your three-dimensional world. And you can also define scale. How big do you want this object to be? Makes sense. Now, if you look at the code examples, what you'll notice is there are actually two ways of setting these values, the rotation, the position, and the scale. One is by calling a set function, in which case you have to specify all three values for x, y, and z respectively. Or you can just say .x equals, or .y equals, or .z equals, right? So positioning is obvious, right? Whatever position you specify is where that object will be. That doesn't require an explanation. Rotation might. So when we say rotation for x, what we mean is if this is the x-axis, rotation is this way. So, and this is defined by radians. So whatever number of radians you define is how much it's going to rotate, okay? If you define the rotation relative to y, that's going to be rotating this way. And if you do z, it's going to be rotating that way. So if you specify rotation for x, y, and z, it's going to be rotating this way, and that way. Got it? Cool, easy. And scale is you specify the factor of your scale. So if you do 1, it means don't change your size, just stay whatever you are. If you say 2, it will scale it by 2, right? So it'll be twice as big. And you have to specify it for each. If you want everything to scale, you have to specify the same value for each parameter. But if you only want to scale x, but not y and z, fine, you can do that as well. Now, one of the really powerful things about having a hierarchy in this kind of an API is that when you apply any of these functions or attributes to one of these objects, it applies it to all of its children. What do I mean by this? Well, consider this. Imagine, again, the car example. right? So in a car, you have wheels, you have lights, and so on. All of these are individual objects, but all you have to do is set a position on the car, and all the lights, the tires, everything will move with the car. You move the car here, everything else. It's not like you move the car, but the wheels stay. Doesn't make much sense, does it? So what happens is every time you move an object, all of its children get that application. If you rotate it, all of its children rotate. If you scale it, all of the children scale. Right? This is really powerful, and you can do a lot with this. And we'll see what happens moving forward. So I mentioned that object 3D is an abstract class, and scene was one of the subclasses, right? Which acts as the root of our tree. It's like document for the DOM. Think of it that way. It's the root of the tree. Mesh is another subclass of object 3D. In other words, mesh is just another object. Now, what is a mesh? A mesh is the thing that you use to describe the stuff, the actual objects that you're going to see in your scene. Every person, every tree, every house, everything that you're going to have, every kettle, every cup in your scene, all of those are meshes. But what is a mesh? Well, actually, a mesh is composed of two things. It's a geometry, and it's a material. Okay? The geometry specifies the structure of the object. Okay? And what does it need to specify the structure? It needs two things. It needs a set of vertices, points in our three-dimensional space, and it needs triangular faces that, connecting these points, create our overall shape. All right? Now, you have to be careful. If you have too many triangles, you will have very high fidelity. It'll look crisper, but it's a performance problem, right? If you have too many triangles, that's that much more that your computer has to do to compute when rendering, right? If you have too few, it doesn't look crisp enough. So you kind of have to find the right balance with how many triangles you use when you're constructing this structure. The second thing you need, okay, so you have your structure, fine, but something's missing here, right? Obviously. And it's like the surface is not painted by anything. And that's where the material comes in. So the material says, paint it with this kind of color, have it be shiny or not shiny, have it be responsive to light or not responsive to light. All of these things are defined by the material. So to have any object in your three-dimensional universe, you need these two things. The structure, the geometry of the object, and the material, the thing you're going to use to shade it or to paint it. Okay? So, cool. So we now kind of understand at an abstract level what it means to have an actual object in our scene that will eventually get rendered on the screen in a three-dimensional way. We'll get there soon. Okay, so let's wait, what? So yeah, so this is if you put them all together. So if you put the mesh together with the geometry, you get this, right? This is the painted version. Okay, so let's have a look at some code. So this is an example of how you might create a geometry. Now you notice that there's this object called 3 with capital letters. The reason why it's there is because, do you guys remember that before we had modules, the way libraries would contribute themselves and make them available to you is through the global scope. Like jQuery would contribute the $, and jQuery to the global scope. If you guys remember, like old people like me, you remember this stuff. Okay, now we have modules, so you don't actually have to, when you get it, when you import it, you can do as, and then you can call it whatever you like, but traditionally people still call it 3. It's just an object with a bunch of function constructors on it and other things. Okay, so we have this 3 object, and what we're going to use is a geometry function constructor. Okay, so we're going to do new to create a new geometry. Fine, we do that. Then you notice that a geometry has 2 arrays, as promised. It has a way of defining the vertices, the points in our three-dimensional space, and it has a way of defining the faces, the triangles in our three-dimensional space. Specifically in this case, so we specified the 3 vertices, and the face is specified by the indexes of the vertices. So in this case, we're saying, connect the first vertex with the second and then the third. And then obviously it loops back. So that creates the triangle. In reality, creating a complex shape means having a whole bunch of these. Now, as you can imagine, sitting there and trying to construct more complicated shapes like this is a headache. You will go crazy. So the Threejs people did you a favor, and they gave you things like this. So there are a whole bunch of geometries that exist out of the box that give you more complicated shapes. So vertices and faces are like primitives, right? This is like the low-level API. The next level after that is things like this. So you can easily create, for example, a geometry, a box, like you can create boxes, okay? By using something like a box buffer geometry, you can create cones, spheres. There are actually lots and lots of these geometries out of the box that you can just use by yourself. So you don't have to sit there connecting triangles, by hand, which takes, of course, a lot of time and energy. The APIs should be straightforward to you. To create a box, you specify, the width, the height, and how deep it is, and you can change that. You can have it be deep, but not, The APIs are almost self-explanatory, so I'll skip it, because you guys know. One thing to note here, notice how the names are box buffer geometry. There's this buffer in every one of these. The reason for this is because the original implementation had things like box geometry, okay, cone geometry. But then they came back and did a second implementation using buffers, which are more optimal. They just run faster and use less memory. So it's recommended that you always use the buffer version, not the older version, which I think is actually going to get deprecated later on. So always use the buffered ones. Okay, so now we covered geometries. What about materials? What about how you paint it, right? Well, it turns out there are, again, different materials that you can use. These are just 3. There are more than this, but these are just the 3 examples, sort of popular ones. There's Lambert, Phong, and Standard. And what's interesting is Lambert is computationally cheaper than Phong, and Phong is computationally cheaper than Standard. Standard is the most expensive computationally, but it looks the best. I don't know if you guys can tell at this resolution, but the Standard one looks very crisp. It looks beautiful, but it's more expensive, so you have to kind of pick and choose. If you're looking for just a metallic material, something shiny, you might use something like Phong. It might be good enough. If you just want a regular material that just responds to light and has color, Lambert might be good enough as well. So what I recommend is try using the cheaper materials first, computationally cheaper, and then if you feel like, no, the resolution isn't quite what you want, then you move on to the standard material. Okay. So a little bit of code. Let's kind of bring it all together. So the first thing when we're creating this tree is we have to create the root, right? So we have to create the scene. Again, the scene is a function constructor hanging off of this object, which we will call 3. So we do new, 3 scene, so we have our scene. Remember again, a scene is an object 3D, so it's just a member of the tree. It's just another member, which means, by the way, you can add a scene to a scene, right? Okay. So next, we're going to create a box. So, we do new 3 box buffer geometry, and we pass in, the width, height, and depth. And then we create a mesh. In this case, I'm using Phong, right? Because I want it to be kind of shiny. You can set the shininess, like how shiny do you want it to be? And there's a parameter. You can kind of move it around and get a feel for how shiny you want it to be. And then you create your mesh. So you do new 3.mesh. And you pass in the 2 values. Because again, remember, a mesh is just a combination of geometry and material together. Easy. Then we set a position. So we set the x and y. So the geometry is, the x and y are exactly as you would expect. The y grows upward, okay? And the x grows that way. But the z grows away from you in a negative way. So in this case, I did negative 60. Negative 60 means push this away from me, 60. Some people get confused there. So the camera initially is at the origin, looking towards the negative z. The positive z grows back. Negative z grows forward. Okay. So now, we saw, so you can create some basic geometries, right? You can create like a sphere, a cone, or a rectangle. Okay, but suppose you want to create like Halo. Or some like really, like a game that really requires complex graphics. No way are you going to be able to sit there and programmatically build all this stuff and try to combine a sphere with a triangle just the right way and have it be beautiful. It's just not going to work. So what you do is you use software, 3D software. So there's Blender, there's 3D Max, there are lots of these. And they allow, they have nice drag and drop tools that allow you to specify the geometry. Right? So all those triangles, instead of specifying individual triangles, you can just drag and drop your way to having a beautiful design. Then, once you do that, you export it, and there are lots of file formats that are supported by Threejs. Threejs has a series of loaders for different file formats. The one that's generally recommended is to use GLTF format, and a lot of these sort of popular software systems allow you to export their meshes and into this format. So then you can load it. Look how easy it is. One thing to note here, though, is that you notice that the loader is underneath the examples directory. A lot of people get confused, because examples you would think are meant to just be examples, not library. But in this case, loaders are under example, so just so you know. So in this case, right, I'm using the GLTF loader. So okay, I import it using module or whatever. I create an instance of it. Notice that the loaders are not attached to the 3 objects. You have to load them explicitly. And the reason for this might be intuitive to you because there's so many loaders, they don't want to load it all up in memory. Just pick the loader you want, leave the rest alone. Okay, so you get that loader, you do .load, you specify the path to the file, it loads, and guess what? The thing you get back has a scene on it. Remember that scene is an object 3D. It's just another object. You take it, you stick it into your tree, your sort of DOM. It's not DOM, but you can think of it that way. It's a tree that represents the data you want rendered later. You attach it, and now it's there. Now, suddenly, in your scene, you have something like, for example, that. Now, well, that's slow. It's because of the connection. On my screen, it looks beautiful. Anyway, the projector. Anyway, so that's actually a fairly high-res, like, nice helmet, like the kind that you would see in like first-person shooter games and stuff like that, right? Now that's beautiful. Now to make that contains over 15,000 triangles, okay? And over 8,000 vertices. Now imagine trying to code that by yourself. You would just never do it, right? So it doesn't make sense. By the way, this comes from Sketchfab, which is a popular website where they have a lot of these 3D models uploaded that you can download, some of them for free, some of them you have to pay for. So you can load them up and into your apps and use them. By the way, this was designed by the Blue Turtle. This is username. Anyway, so moving along. Okay, so we can add meshes, which are these sort of structures that have a way of shading them. Fine. The next thing is light. Light is also a thing that you have to add to your scene in order for it to exist in your three-dimensional world. Now, there are lots of different lights, and let me just go through a few of them just to give you an idea of how these things work. So there's ambient light. Ambient light means it applies the light kind of evenly across your entire scene. Right? It just sort of illuminates everything evenly. And you give it a color and how strong you want it to be, and you get that light. Fine. There's point light. Point light is like, you can think of it like a light bulb, okay? You put it somewhere in your scene, wherever you position it somewhere, and then it just projects light out of itself in all directions, just like a just like a light bulb, okay? Then we have two lights that have direction. There's directional light, but regular directional light actually just emits rays that are completely parallel. Like they just come in like this, kind of like the sun. You can almost think of it like, it's actually often used to represent the sun. And then you have spotlight, but spotlight actually projects out like a cone, like this. Projects it out. Both of those require you to specify the position of the light and the target, which will define the angle at which it will throw the light. It will emit the light. Okay, so moving on. By the way, all these code examples, they're almost, I'm not going to go through every line, I don't have time, but it should be obvious. If you guys have questions, tell me later. Okay, so a group. I think this is important to note. So you know in DOM we have a notion of a fragment? You guys know what a fragment is? It's an element that never gets rendered. It's an element that whose only job is to have children in the DOM, right? React uses this a lot with like the empty braces and stuff. Okay, so this is the equivalent of a fragment for this. A group is just an object in your tree whose job it is to just have children, okay? Why would you want this? Well, imagine you want a group that represents a player. Now that player underneath them might have a mesh that represents the head, the arms, the feet, all of these things. But at the root of it, you just have player. And if you want to move the player, you simply move the group, and all of the children, the hands, the arms, the feet, the gun, move along with it. Okay? So it's just a way of grouping elements together. It never gets rendered in your scene. Lastly is our camera. Guess what? The camera, which is the thing that you're going to be looking through when the scene is actually drawn on your screen, it's the angle, it's the position, it's the viewing position from which you're going to look into your 3D world that you're creating. It itself is also an object 3D. It's a subclass of object 3D. Now, there are two kinds of cameras that I know about. One I won't talk about because it's for doing 2D, and we don't care about that today. And the second one is for doing 3D. So this is the one, and it's known as the perspective camera. So to create a perspective camera, the constructor takes 4 arguments, okay? So it takes the vertical field of view. So if you think about it, the camera, if it's got like a rectangular thing, right? It sort of looks out in this direction and in this direction. It looks out like this and like this. This angle here, this is your vertical field of view. This would be your horizontal field of view. So if you make a very big vertical field of view and a bird flies over, you will see it. If you make it really small and a bird flies, you won't see it. Got it? Okay. So that's the vertical field of view. There's the aspect ratio, which is simply the ratio width to height. Okay? So you just do width divided by height of whatever canvas you want to render on, and that's what you get. And then you have the near and far planes. The near plane is the closest thing that your camera is going to render. And then the far plane is the farthest, so it renders all the stuff in between. This is kind of what I'm talking about. So in this case, we have the camera that's projecting out into our 3D world. That first clip, that first rectangle with the 2 circles, that's your near plane. Anything between the camera and your near plane is ignored. It never gets rendered. And it's only between that and the far plane, all of that stuff in between, and that within that vertical field of view, and of course with the horizontal field of view, only that will get rendered. Furthermore, one of the things you'll notice about this kind of camera is it will render objects that are farther, smaller. Even if they're the same size, if one is farther, it gets rendered smaller. So this gives a 3D view of your universe, right? This is how we see things. Okay. So, wait, I want to say a few more things because we got time. So remember how I said that a camera is an object 3D? How cool is that? So remember that objects inherit kind of the behavior of the parent in that if you rotate the parent, all the children rotate. Suppose you're making a first-person shooter game, right? You have a mesh which represents the person, or maybe a group with a bunch of meshes inside that represents like the head and the arms and so on. And this is and he's got a gun, and this is your player 1, right? What you can do is position a camera right between the eyes of your player. Okay? Now, when you move your player, guess what? The camera goes with the player and the eyes and the ears and everything else. It's just another object. So now suddenly you're moving around and the camera is just looking everywhere where your player is looking. So that's how you can do a first-person shooter. Yeah. That's really cool stuff. And by the way, if that first-person shooter, I'll tell you that later. Okay, so now that we have this notion of this tree that has information about mesh, which has, remember, geometry material. It has light, and so far we also talked about mesh, light, and camera, right? That's all we talked about so far. Now you want to actually render it on your screen. Well, we're living in a browser, so if we're going to render stuff, we might as well render it onto a canvas. Okay, so what we need is some sort of a render, and then one of the renders that exist is the WebGL render. So underneath it uses WebGL, which then renders to canvas. So that's what we do. We create it. So in here you can see that we construct a WebGL render. We pass in this, there are more arguments you can pass, but these are the ones I'll talk about. The canvas, this is the canvas it's going to draw on, fine. and anti-alias true. I'll explain what that is in a bit, but basically it makes the edges smoother. And we'll talk about that in a moment. We specify the rendering size. This is basically the size of your canvas. And then we say, okay, render. Like, go, draw. And we give it two arguments. We say the scene, which has all the information about our three-dimensional world, and the camera, which specifies the perspective. Why do you have to specify the camera? Because you can have many cameras. In a first-person shooter, remember, you have a camera here. They're playing, and suddenly your player dies. And you go, the player's like, why did I die? Well, if you're maintaining state about your game, you can replay your game, but now, when you're rendering, render from a different camera, a camera that's maybe zoomed out. And suddenly, they look at the same game, exactly what happened, from a different perspective, and they see that a bullet came from the back, hit him in the head, and they fell down and died. Yeah? So remember, a camera is just a different perspective, and you can have multiple of these in your game. Okay, so I talked about anti-aliasing. What is that? Well, if you think about it, at the end of the day, what is a renderer doing? It's got geometries, shapes, it's got pixels, and it's trying to sort of fill pixels based on the geometry and the material in order to fill them. So let's look at this example. Can you guys see the grid underneath it? Let's make it. Oh, okay. So let's say we want to fill this triangle, right? So like a basic way to fill it is to simply say, okay, any pixel that this triangle either intersects or encompasses, we're just going to fill with whatever material color that we chose, which let's say is yellow. Fine, we can do this. The problem is we end up with very blocky edges, as is the case with this font. So this font doesn't have anti-aliasing. This font uses this kind of an approach, where it just fills in the blocks of the pixel, and it doesn't look very good. What anti-aliasing does is this. It's saying, okay, if the pixel is inside the triangle, fill it as normal, fine. But if any of the lines pass through the pixel, fill it with a slightly lighter color. Okay? And what you end up with is this sort of smoother edge, and that's the font, kind of, like that font has anti-aliasing. It's got like this blurry part at the edges, which when you zoom out actually gives a nice smooth edge. So that's anti-aliasing. So anti-aliasing true turns that on. Remember, nothing is free. Everything requires a computational price, and perhaps a price of memory as well. So it's always a good idea to try it without anti-aliasing, then try it with, and see what the best, because you understand it's not free. If you use it, you pay a penalty. Okay, so animation. So we talked about how to create a renderer, fine. So you can do, new 3 WebGL renderer, okay. We specified the size. To do animation, it's actually quite simple. You create a function, you call it, and then inside the function, you're going to do request animation frame, and then pass the function, so it calls it again in a loop. This will call your function every time the browser wants to re-render itself, okay? And typically, browsers have a frame rate, so this will keep getting called. I kept mentioning performance and processing. Remember that JavaScript is a single-threaded system. It's a single-thread environment. So if you end up going off in one of these renderers and doing lots of computation, you're going to slow down the rendering of the entire browser. And if you're doing animation, you might end up seeing jitters, or it might freeze, and it won't look very good. So, so it might. Thank you. So that's not a good idea. So you really have to take this into account when you're doing your work. Now, in this case, if you notice, in the render function, what we're doing is we're rotating a mesh. Okay? So we're rotating a mesh around the x-axis, the y-axis, and the z-axis. Then we're telling the render, okay, now that we've changed the scene, render. Then later, we change the scene again, render. Then later, we change the scene again, render. And voila, we end up with animation. That's how the whole thing works. And that's, oh, wow, you really can't. Can you guys see that? So, look there, that looks better. Yeah, okay. It's a cube rotating. Sorry for the lighting. Right, so this is basically how this stuff is written. Now, all the code for rendering this, actually, for doing this whole thing, is defined here. Let's go through this very quickly because you're all now experts in Three.js, right? We got this. This is easy. We import Three.js. Boom. And by the way, you see how it says as 3? You can do as hopar. It doesn't matter. As whatever you want, and then you can use hopar.scene. Okay. So you import it. Next, you create the scene, then you create a geometry. In this case, we're creating a box. We used a box buffer geometry. Specify the width, height, and whatever, then the depth. And then you also specify the material. In this case, I'm specifying a standard material. I'm specifying the color, what the metallicness should be, like how shiny should it be, what the roughness should be. All of these things you can sort of play with to get a feel for how these things change visually. And then I do scene.add. In other words, I add it as a child of scene, where scene is an object, right? Next, I create a light. In this case, again, a directional light. I specify its position. I specify the target position, which is where the light should go. And then I add both of them. In other words, the light itself and its target as children of my tree. In this case, children of my scene. And then I create a camera. Again, I specify field of view, the width to height ratio, the near plane to far plane. I specify, the position of the camera. So in this case, I don't change the x. I raise the camera up. The camera begins at the origin, so 0, 0, 0. I raise it up 300, okay? And then I go back 300. Not forward, but back 300. Because remember, negative z is in front of me. So if you guys are looking at the screen, negative z is in that direction. So 300 means go back. Take the camera and bring it back. Okay. So that's what that does. And then we have our animation code, which is exactly what you saw before. Easy peasy. All right. Next is interactions. So we understand that we can paint three-dimensional information onto a canvas. But how do we actually interact with it? How do you click on a box that you rendered or mouse over it and get an event? Remember, this is not the DOM. You can't just attach an event to some element and then get these magical events. This stuff doesn't exist on Canvas. So what do? Well, you do something called ray casting. So the way ray casting works, and by the way, you don't just understand how it works, and then I'll show you the code. So the way ray casting works is this. On the screen, you specify a position. The position can be where the mouse is or where the bullet was shot. It doesn't matter. Some position. And then you cast a ray out from that position relative to where you are with your camera, straight. And any object that is hit by that ray is added to an array. And then you get back an array. Okay? So if there are 3 objects along that path, it will intersect all 3 and return them as one array. The closest one will be the first one in the array, or index 0. The farthest one will be last in the array. Okay? One important thing, though. The ray casting that is done by Threejs uses a different coordinate system from the one your browser uses. So your browser, if you remember, begins with 0, 0 at the corner. X goes this way, but Y grows this way, right? Whereas the way the ray casting system works in Threejs is it puts 0, 0 at the origin in the middle, right? In the middle of the entire thing. And then it goes up all the way to 1 and down to -1. And then 1 and -1. Okay, so it looks kind of like that. So what we have to do is when we receive mouse event, we have to convert those coordinates from the mouse, that coordinate system, to this other coordinate system so that we can use the ray casting mechanism in Threejs. So looking at this code here, so you can see I create a raycaster, so 3.raycaster. Then I don't want to get into state management, so for now I'm just creating a variable that I'll use later, a global variable. You might use Redux or whatever state management you're using to maintain state about your app. Or your game. Right, so you do mouse 2D, whatever, you can call it whatever you like, hopar. And then we do window.event listener so that we know when a mouse moves. This is just basic browser development. This has nothing to do with Threejs. But then when we receive the event from the mouse, we do event.client X and event.client Y will give us the coordinates of the browser, right? But then with this formulas that you see here, and these are literally just copied and pasted from the Threejs website and their documentation, you do a conversion to the X and Y that is relative to that other coordinate system where the zeros are in the middle, and it goes all the way to 1 and -1. Okay? So that's the first part. That's just a little bit basic math to make the conversion. Once you have that conversion, then in the render function, you can say, okay, raycaster, this thing I made, set from camera, and you specify the location and the camera. In other words, you're saying, hey, Raycaster, this weird thing that's going to launch this cool laser, put your laser at this position relative to this camera, okay? Then you do intersect objects, which is like cast the array, and bring me back all the objects in the array that I give you that are intersected by that line. So what that means is, let's say you have a two-person shooter and they're just shooting at each other, and all you care about is if one hits the other. You can just pass in those two objects, and it will just tell you if one of those players was hit back in the array. And if they are, then dead, you change state, and then you animate them dying, or something like that. And the rest is just basic animation. Now, in this case, this code right here will just, whenever you mouse over something, it will turn that red, and it will leave it. For a demo, what I've done is I've also added some basic code that simply checks, well, if it's not mouse over, make it white. And by doing this, again, are you guys going to be able to see this? Let's see. So I moused over it, it turned red. Wow, the animation sucks. This projector sucks. Anyway, so you have an animation, you mouse over it, it turns red, and then you move the mouse over. You get it. We can, yeah, okay. That's it for me. Thank you so much.